باسورد دكتور. هلو. اوكي دكتور.
هنبتدي كمان 14 دقيقة. اوكي
خلاص اوكي ان شاء الله.
probably 7 minutes. Everyone, am I audible to everybody? Do you guys hear me well? Am I audible?
Yes, doctor, you're clear.
Perfect. All right. Today we're going to be starting the topic of artificial intelligence and machine learning. Okay. What do you expect from today's lecture? What is expected is to know what artificial intelligence is in general, what is machine learning, what is the difference between the two, okay? So what is the difference between artificial intelligence and machine learning? Is there any difference, really? Is there any difference? And if there is, what would that be? And then we're gonna be learning different algorithms, so to say, from artificial intelligence and machine learning. We're just gonna go through them quick, and then next session we're gonna be starting our very first algorithm that is really, really important in machine learning and data science. Okay, so today what you expect is to see a general overview of what machine learning is, what artificial intelligence is, and how we can get benefit of this. For my senior project students, this is very important for your defense, which is going to be in 2 weeks or 3 weeks. Okay, so this is very important because if you're asked, why didn't you do this, or why didn't you use this, and why did you use that, you should be able to answer those kind of questions. All right, let me share my screen. All right, here it is. The very first question that we should ask ourselves, what is the definition of artificial intelligence? Okay, what is it? Is there a concrete definition for artificial intelligence? And the answer is not really, because every big concept doesn't have a unique agreed upon definition. So if I ask you what is smart city, there is no single definition for that. It depends really on what you want to do in smart city. Okay, even IoT and so on, you would find some definitions that are not really broadly agreed upon. So hello, do you hear me well, everybody? Do you hear me well?
Yes, doctor.
Okay, sorry. Let me continue that. So we can say in general that, AI is having the machine to act humanely, okay? Or act rationally, or think humanely, or think rationally, okay? This is very, very broad definitions that you can actually give for AI systems or machine learning systems. And as you will go deep into this through this workshop, you will actually feel that those definitions are very, very abstract. They don't really represent what you will be able to do when you start learning this. So I have a question here, same as robotics. If you're asking about the definitions, because I just saw your message, if you're asking about the definition, yes, of course. The machine is kind of a robotic, right? The robot is kind of a machine that is equipped with something that you want to do. And most robots now have AI systems and machine learning capabilities embedded in, because nowadays robots, by definition, they would have some kind of AI and or machine learning capabilities, okay? So AI can broadly be classified to be either narrow AI, okay, or general AI, narrow or general. What is the difference between narrow AI and general AI? The narrow AI is when you want the machine to learn one task and to be great in this task, and that's it. You don't want the machine to be very intelligent in everything, okay? You want the machine to do, let's say, Google search. So the Google engine is smart. It's very smart, but it's very smart in searching in the web and so on and so forth. So that's what the Google search does. Let's say image recognition. Image recognition is very smart, but in just image recognition. So it can actually help you recognize certain image, but that's it. Okay. Self-driving vehicles, right? Yeah, the vehicle is very smart in getting you from one place to another, safe. It tries to find the best route. It tries to keep you safe by not doing accidents. It predicts the movement of other cars around it and so on and so forth. Yes, but that's it. When I say that's it, I'm not saying that what it does is very simple. No, it's very complex, but yet it's narrow AI because it was developed and designed to do just this task. The general AI is represented in that robot that we all know. It's called Sofia. Okay, I don't know if you guys know about Sofia. She's a robot that got the Saudi nationality a few years ago. So she's so humane that, the Minister of Foreign Affairs of Saudi Arabia was in a conference, and then he actually, was impressed with her capabilities, and he announced that the Kingdom of Saudi Arabia is giving Sofia the citizenship of KSA. I heard some, I was watching a kind of a debate between her and a TV interviewer, and she literally outsmarted him by far, by far, that's really was impressive, her capabilities were way, way, way more than, and she also had culture, because when I say culture, I'm talking about jokes. Sarcasm is culture, the ability to do sarcasm and so on. That's culture. And she literally made sarcasm about what the interviewer was saying, and she outsmarted him. And, yeah, that's general AI. Now, the robot is literally acting like a human. Not only that, but the machine is self-learning. So, you don't need now to tell her what to learn or what not to learn. No. Sofia is learning by herself, reading the whole internet, the encyclopedia, whatever, and she's gaining a lot of information that we cannot gain, basically, because, her capability of her learning and dedication, is literally, enormous. That's scary, I agree. It is scary. I also, she's so smart that I was actually following her on Twitter. She tweets a lot, That's why I stopped unfollowing, I unfollowed her because she tweets a lot, but her tweets are very smart. If you want to get impressed, follow her on Twitter. She's really, really smart in her tweets, you know. So now, how and where do we actually use AI? In which domain? In probably everything that you do nowadays. So vehicles, in the, of course, the internet, the cloud, satellites, the mapping, the smart houses. I have one engineer today with us who actually did the smart house as a senior project graduation, Yara, and her project was really, really amazing. Also, something like, you know, whatever that you can think of, now AI is involved. E-traffic, you know, transportation, whatever that you can think of, you will find it now managed by AI. Your phone is managed by AI, basically. You can actually adjust your phone so that, you know, it recognizes your face and let you in without, you know, putting any password or whatever, right? So last year, I had a student, an amazing student who worked also in e-traffic. So last year, I had two senior projects. One of them was the you know, smart houses. We have one engineer with us today, Yara Khuderi, who actually did that. And another project, e-traffic, that was also spring 2020. And I had an amazing gentleman who asked a real question that was really hard to answer. You know, what was that question? He said, well, it wasn't really a question, it was a comment. He said, I hope it's real AI about the lecture that I was going to be giving, right? So he was like, I hope it's real AI. I hope it's not just a search tree. That was an amazing thing to say, okay? And that's why I had to stop on this comment and discuss it with all of you. So, are they secure? About what, Mariam? I'm sorry, I just saw it. Are they secure? AI in general, that's hard to answer, right? But if you don't trust AI, then you shouldn't be trusting security, because now security became so complex that it needs AI. You know, so now security itself is equipped with AI to make systems more secure. You know, and I'll talk about that. That's a very good question, Mike. So when we talk about that, we need to know the difference between learning and intelligence. Is there a difference? Absolutely. Absolutely. Every learning is intelligence, okay? But not every intelligence is learning, okay? It's kind of. So let's see that. If you look at this, when you play chess with the computer here, okay, you have here intelligence, kind of, we're mimicking intelligence, but we're not really learning here. We're not. We don't learn anything. What we do is we evaluate the situation, and based on the situation, here we actually choose our move when we're talking about the chess, okay? Do we learn anything from games? It depends, but usually no. I mean, it depends on the state space that you have, and you choose your best move based on the situation. Another example is here. Do you see? In this one, the X and O, can you make an intelligent one? Yeah, but there's no learning. The rules are the same. You apply the rules, you win, basically. All right? But you don't learn from previous experience. You don't learn from history. How about the maps? Oh, yeah, there is intelligence, of course. You get the minimum path between two locations based on time, based on distance, whatever that you pick. But in the end of the day, you know, the you get the solution, all right? And you have studied that in networks, by the way, something like Digestra. So you have an approach to follow that gives you the feeling of being smart, okay, but there's no learning in it, okay? How about this, the expert systems? Expert systems, it's one of the big names about artificial intelligence components is called expert systems. Expert systems is basically when I have a very clever one in certain domain, let's say, I don't know, a doctor or something, and I cannot have this doctor, you know, see patients in many, many different locations, you know, to see what's going on with their health and so on. So I take all the knowledge that he knows in the form of rules, frames, whatever, and I put it in a system called expert system. And then the expert system will be distributed in many, many places. And therefore, as if I cloned the doctor into many, many people, and I put them in different locations. Okay, so this is also one of the ways that we have to make intelligence. Okay, all I talked about so far is very old artificial intelligence. Okay, as we go, you will find the really, really interesting stuff when we start making a brain as an example. So to answer the question about the search, you know, we have some search techniques that some of them you have seen in the courses that you have studied, like data structure. You have seen something called depth first. You have seen something called breadth first. There is something called best first, A star, and so on and so forth. All of those algorithms are search techniques. They're not really like back in the 1980s, that was the artificial intelligence, you know, because it used to solve the problems that people cannot really write programs for. As an example, let me give you an example of that. If you have something like this, you know, and I ask you to put 8 queens in this board, okay, without having 2 queens to check each other. If you don't know chess, to check means both of them are in the same diagonal or in the same row, okay, or in the same column. So same row, same column, same diagonal. So if you want to distribute 8 queens on this board so that no 2 queens is this symbol, right? If you don't know chess, this is the symbol. To check each other, you cannot really write a program for it, a normal program. Okay, you can't. Why? Because this is not a traditional problem. We call it an NP complete problem. Okay, so it's a problem that needs a different way of solutions. One of the solutions that you can get is using the those kind of search techniques. And back then in the 1980s, that was the AI. Like if you learn how to do search techniques now, you know, artificial intelligence. Of course, after 40 years of that time, those kind of search techniques, you know, they're really legacy. I mean, you know, they're still in use, but they're not really considered AI whatsoever. All you do is search the whole search space or some of the search space, depending on the search algorithm that you're adopting. Just like when I take you and I put you in a maze and I ask you to get out of the maze, right? If I ask you to get out of the maze, you can say, okay, you know what? I'm gonna get all left because I don't know the maze. You know? I'm gonna go all left, and at some point of time, I'll get out of the maze. And you're right. If you take all left or you take all right, you will get out of the thing. Of course, this is a way of artificial intelligence. I mean, it used to be artificial intelligence in the 1980s, but it's not really anymore, okay? Before I go and tell you about the different types of artificial intelligence. Let me ask you if everything is clear. Can you please let me know before I move on?
Yes, doctor, everything is clear so far.
Okay. Now, the artificial intelligence, and that would be very interesting probably for one of my groups here. Okay, the e-host. You know, the word artificial intelligence include inside it the machine learning, okay? So, you know, machine learning is artificial intelligence, but artificial intelligence doesn't have to be a machine learning. So if you think about this, you would find that the artificial intelligence is the superset, and the machine learning is the subset, okay? That, here it is. Now, the artificial intelligence can be machine learning, and the machine learning can be broadly divided into something called deep learning, which I will teach you in one of the sessions. Deep learning, which is the thing that opens the unlimited power of artificial intelligence, the deep learning. Supervised learning, I'll tell you what it is. Unsupervised learning. There is also in machine learning something called the semi-supervised learning. It's not in the graph. You can also have within the machine learning something called regression, which I will be talking about in the next session in details. Artificial intelligence could also be natural language processing, NLP. Okay, so you can do classification of the statement, the content extraction, the machine translation, answering questions, text generation, so speech to text, text to speech, and so on and so forth. That would all be among the natural language processing. You have also expert systems, okay, which I'm not going to be talking about because, you know, it's not, it was the thing in the 1990s. My graduation project in bachelor was an expert system to do routing in a computer network. But that was, yeah, I shouldn't be saying that, 25 years ago, anyhow. Okay, that's 25 years ago, the expert system. So I don't see it now as something big that we need to talk about anymore. The vision, computer vision, and in my groups here, two of my groups, the people who are the group that are making the elevator, the smart elevator, and the other ones who are making the e-host, you both use vision. And the ability of vision is for the machine to see and comprehend, right? See and comprehend. So the vision could be image recognition. So if you see a cat, you know it's a cat. You know, if you see a dog, you know it's a dog. You know, it's also machine vision in general. So the machine can see, you know, can act with vision the same way a human acts with vision. So it could be just recognition or even farther, you know, a continuous vision for the machine. Again, the speech here, which comes to under the NLP, you can make it as speech to text or text to speech. Also in AI, you can do planning, you can do robotics in general, and so on and so forth. That's the different branches of artificial intelligence. This is the tree of applications that you can do with artificial intelligence. Of course, this tree is very, very limited, right? You can actually add more to it, like, you know, e-health and so on and so forth could have different branch because it's very different from everything and so on. It could come under planning, maybe, you know. Anyhow, so those are the things that you can do with artificial intelligence. Now, Machine learning. Machine learning could be supervised learning. What does it mean to be supervised? It means you bring the input and the expected output to the machine. Just like how you teach a child, you know what? 2 multiplied by 3 is 6. So you give the child the input and you also give the child the output. That's why it's called supervised learning. You tell me, okay, if you're gonna be giving the input and the output to the machine, where is the intelligence here? You're telling the machine everything. Yeah, well, just a second. Yes, you're teaching the machine a sample, but the machine later is able to normalize this sample on everything. So when you teach the machine 2 multiplied by 3 is 6, and 3 by 4 is 12, and so on, later on, if you teach the machine well, if you ask the machine any 2 numbers that you have not taught before, the machine will be able to answer, okay? The machine will be able to answer your question. So this is supervised learning. Of course, I'm talking about here multiplication. We don't teach machines multiplication because it's not really a problem that suits the artificial intelligence. It's a very simple problem that doesn't need the big capability of AI. I'm just giving you an example, okay? The unsupervised learning, however, you don't give the machine the input and the output. No, you give the machine the input and that's it. That's it. And then the machine deals with the input to figure out the output. How? I'll talk about it soon, okay? There is also something which is not here. I don't know why. It's called semi-supervised. Semi-supervised, which takes the flavor of each and every one of them. So it takes some flavor from the supervised and it takes some flavor from the unsupervised and becomes semi-supervised. So the semi-supervised have many, many shapes and behaviors. One of them is to teach the machine in the beginning and then leave the machine to continue learning by itself. So in the beginning, it becomes supervised, but then by time it starts to be unsupervised, okay? So this is the semi-supervised. How about the reinforcement learning? I always call it the stick and carrot approach. Stick and carrot. Or let's say a chocolate and time out, okay? So if you have a child that you want to teach, you leave the child to act. Then if the child does a good thing, you give the child a chocolate. If the child does a bad thing, you give the child a timeout. So next time, the child will avoid having timeouts by avoiding doing what they did to deserve the timeout, okay? Now, when you're talking about data, usually supervised learning, unsupervised learning, and so on, great. Reinforcement learning, at least I see it this way, okay? This is my personal opinion. It suits best for deciding which action you want to take, okay? Data, even though it is possible to apply reinforcement on data, but it's not the best method. Why? Because reinforcement learning requires to deal with the surrounding environment, which means to apply actions. Again, this is how I see it, okay? You don't have to follow the way I see things, but if I have actions and I want to teach the machine to decide which actions to take, I will definitely equip this machine with reinforcement learning capabilities, okay? You don't have to follow, my philosophy of seeing things, but I believe that this is the best choice for actions. Now, there is something called deep learning. And the idea behind deep learning is not just learning. You actually do deep learning to extract stuff that even us, human, we don't know. So in other words, when you're doing deep learning, Hassan, I'm really sorry, everybody. I should be seeing the chat. I really apologize. Let me answer Hassan's question. That's a good question. Like teaching a machine 20% of the data set and test on the rest. No. Is this question about the semi-supervised, Hassan? Is this question? Oh, supervised learning. Absolutely. Yes, that's what we do, Hassan. Absolutely. It doesn't have to be 20 and 80. It depends on the data you have, right? But yes, you divide your data sample into two pieces. One piece you use to teach the machine, the other piece you use to test it. You're absolutely right. Okay. So that's the deep learning. Deep learning is different from the normal learning by deep layers that we have. We have more layers, as you will see. And that helps us that the machine will extract stuff that we ourselves don't know. As an example, if you're feeding to a deep learning approach, RNN or something, data that shows you how you set up your store, so which goods come beside which goods and so on. And then you provide information like, you know, how much you, earned this day or this week or whatever. And you will find that the deep learning will give you advices that is very weird. Something like, if you put shoes beside socks, you will sell better. If you put food beside drinks, you'll sit, you know what I'm saying? Something that you didn't even expect to have from the machine. Something that you didn't, it wasn't your target to have. So you will get your target and much, much more information that the machine will basically teach you how to do stuff in a better way. How do we do that? Using deep learning. And we also, just like how we have supervised and supervised, and we have deep learning, which is also supervised and supervised, we have reinforcement learning and deep reinforcement learning, which actually we use to, same idea, learn much more than what we expect. Okay, so this is a very high level, classification of the machine learning techniques. Here is another one I found. Just to be honest, I did not draw this. Okay, I got them. All right, I just didn't add the reference. I will definitely. Here, also another classification that I like from machine learning. What is it? The machine learning could be unsupervised learning or supervised. Okay, let's go for the supervised side first. In supervised learning, we have labels, as you can see. Okay, labeled data. So we say, as an example, if you have this much of money, then you can call this little. And then if you have this much of money, then you can call it moderate, and so on. Those are the labels. You start labeling your data sample. And then, you have a goal here in the supervised learning, which is you need to predict. I saw a study about machine learning that they put beers and diapers together in Walmart, okay, because they said 80% of fathers will buy beers when they go shop for babies. Yes, I mean, it could be very true, right? Because this depends on the statistics, and the mathematics, it never lies. Yeah. you know, headache with the babies, father wants to forget. Yeah, makes total sense. It makes total sense. So here, the supervised learning, it can also be divided into two things, and as you can see, categorical labels or numerical labels. Okay, what does it mean? It means that when you want to do regression, you can do regression supervised. Of course, you can do it unsupervised as well, as you will see. Okay, and classification, you also do it supervised. If you want to do regression, you can use the actual regression algorithm. You can use SVM regression, which is, you know, supervised vector machine, and you can use neural network regression. I'll teach you all this in this workshop. Okay, it's going to be much longer than the database one because each and every leaf that you will have, you see here, will have its own session. Okay. Next time, I'm going to be starting with this path: supervised learning, regression, regression. And in regression, we should have also two different categories: single variable regression and multi-variable regression. Next time, I'm going to be starting with single variable regression, you know, and then the time after, I'm going to be explaining the multi-variable regression and so on and so forth. We're going to be starting with this regression part, then the classification part, and then when we're done with all supervised learning, we're going to be going to unsupervised one. I cannot start with unsupervised because unsupervised is much harder. Okay, so I'm going to be starting with this subtree, the orange one, and I'm going to be going from the sorry, I hope it's not Corona. Here from the supervised learning, I go for regression, and then, you know, regression, SVMs, and the neural networks. Okay, you can also do classification. So what is the difference between regression and classification? Regression is to predict, you know. So if you want to know whether it's gonna be raining tomorrow or not, like the forecasting that happens, how do you do it? Well, what you do is you have history, of course. You should be having history, and you learn the history, and based on the history, you inject data, and injecting the data will tell you most probably, or with this probability, it will be raining, as an example, right? So you send the pressure, you send the humidity, you send, based on how you learn the regression model, as I will be showing you in a few slides from now. We also have something called SVM. SVM is very strong. It's a statistical approach. I know people hate statistics, but I'm hoping throughout those workshops, you know, you will love mathematics, because the problem with teaching mathematics in general, people learn mathematics without knowing what is it, like what is the benefit of learning this. That's what happens when we teach dry mathematics, right? Dry. But if you see the mathematics giving you intelligence, makes the machine more intelligent, I'm hoping that you really start liking the mathematical models that I'm going to be introducing. The way I'm going to be working, by the way, I'll introduce the theory, the mathematical models, and then I'll show you how you can do it using Python, okay? And the libraries in Python and so on. So I need you all to get your hands dirty with those approaches in Python. So here it is. You have also the SVM, as I mentioned. You have also neural network. What is a neural network? A brain, a small brain. A neural network is a small brain, okay? All right, how about the classification? Classification means, you know, to divide stuff into different classes, right? I remember the smart home, Yara, she did a very interesting classification approach. She used a probabilistic classifier to put energy consumption into different classes based on the, correct me if I'm wrong, Yara. Yes, the basic classifier. Thank you so much. You know, and I'll be teaching you all the basic classifier as well. It's called naive basic classifier. It's not really naive or anything, but I'll talk about it when I start presenting that. So, and we have something called, you know, the K-mean. We have different neural network approaches and so on and so forth. That would be for also classification. You tell me, but we have here neural network in the regression. I'm really sorry. We have here a neural network in the regression. Yes, we do. With neural network, you can do a lot of stuff. Neural networks, which is the brain, have a lot of capabilities. You can use it for classification. You can use it for regression. You can use it for clustering. You can use it for many, many, many things that you actually face. Consider it an actual brain, okay? You can use it in many, many things, as you will see later. So this is the supervised. We have here the unsupervised. Here the data are unlabeled, okay? And it basically clusters or reduced dimensionality. What it means, I'll talk about it in details when I explain it in a separate session. But for now, clustering means you get things that belong together in its own cluster or group. You know, if you look at the AOM students, you can actually subgroup them to engineering students and let's say management students. And then the group, the cluster of engineering students, you can divide it into computer engineering cluster, electrical engineering cluster, chemical engineering cluster, and so on. This is what we call clustering. And yes, the neural network and the machine learning in general with different approaches can do that, you know. And there's something called dimensionality reduction. I'll talk about it when you know, you understand the supervised learning, because that's a little bit not an easy concept to talk about now. All right, so far so good. Am I too fast? Is everybody following? Is everybody following?
Everything's clear so far, Doctor.
Okay, great. Perfect. Now, as I mentioned, the learning, we have supervised learning. You give the input and the expected output. Put under the expected many lines. Why? Because when you start teaching the machine, it will never give you the output you want from the very first time. You need to learn, teach it and teach it and teach it and keep teaching it until you get the expected output. How do we do that? Depending on the approach. If you're using neural networks, I'll show you how you do supervised learning in a neural network. You're using a regression, I'll show you how you do supervised learning in regression, and so on. Okay, so what you see here are basic concepts, right? This is not a mathematical model, it's a concept. And then this concept, you can apply it in whatever, you know, machine or approach you want. So regression has supervised. Machine learning, neural networks has supervised, and so on and so forth. Each and every one of those approaches have its own supervised, unsupervised, and so on. I just want to stress on something, even by the way, you know, master students or even PhDs sometimes mix between the unsupervised and the reinforcement. And I totally understand why they do that. Okay, the mix comes from the fact that both of them, you don't give them an output. Like the supervised is very clear. You tell them, if you get this input, you should be having that output. That's supervised. The unsupervised and the reinforcement, they're very close to each other in the way that none of them takes the expected output. There's no expected output here. That's why they mix. So they're very similar, but they cannot be more different. They cannot be more different. They're very different. Why? The unsupervised goes for certain goals. Okay, something like clustering, So you divide clusters, and the reinforcement learning gives you a plan. That's why I said before, and this is my own opinion, if you want to go for any other opinion, it's totally up to you. But the way I see it, reinforcement learning really gives you a plan. So it gives you a sequence of actions to execute. So as an example, if you have a robot, and this robot wants to go from location A to location Z in a grid map. So the robot can move to the right, can move to the left, can go forward, and so on. Okay. Then the robot goes left, finds out that the robot is facing a wall. Oh, so that's not the right action. So it gives negative value. Remember, I told you either time out or chocolate. It will give time out for this action. Okay, it will give a negative value for it. I don't want to do this again. So it goes back and tries different action and so on. The outcome of this process is a sequence of actions the robot is taking to reach certain goal. So do you see? Totally different things. Unsupervised learning can actually classify you guys as AOMers, who's computer engineering, who's HR, that's, clustering. But the reinforcement learning, no, it gives you a plan, a set of actions, a sequence that you need to follow in order for you to reach what you want. Let's see, Hassan, when it comes to supervised learning, we can easily calculate the accuracy of the machine prediction. Absolutely yes. Why? I'll tell you why. Thank you, Hassan, for this. Hassan is saying, when we're talking about supervised learning, okay, we can definitely calculate the accuracy. And yes, true, absolutely. Yes. How? Because basically, the expected output. And you can definitely measure the output that you get from the machine. So the difference between, it's not really the difference, it's the square of the difference. So the square root of the sigma of the output minus the expected output square, that would give you what we call the total expected, the total error, the mean square error, basically. And the mean square error calculates, or it's a measure of how accurate your machine is. That's a beautiful question, Hassan. Hassan, I taught you something before, right? You graduated already, right? Yes, that's right. I remember, yes. So the rest of the question that Hassan is asking, how can we use unsupervised reinforcement or reinforcement learning to make a plan without knowing the accuracy of the output? That's a beautiful question. The answer is, if you don't mind, let's see it when we talk about it. Why, Hassan? Because that's all about the unsupervised learning and it's all about the reinforcement. As an example, for the unsupervised, Yeah. Well, no, I'm gonna give you an answer, but it's not gonna be a very complete answer. It needs a whole session. This is what the learning is. But in case of unsupervised learning, what we do here is, as I mentioned, you do clusters, right? What is this cluster? Many points. So how would you calculate the accuracy of something that is gonna be getting added to it? How far it is from each and every point. That's one of the learning algorithms. How far it is Euclidean distance. It's an Euclidean distance over the XY plane. Or you can actually get the central weight of the cluster, okay? And also it's something called central weight, I'll talk about it. And then you measure how far the point that you want to add to the cluster from that central weight, okay? I hope this is, enough answer for now. We will have a complete session about it, okay? That's for the unsupervised learning. Now, the same applies for the reinforcement learning. If you're doing reinforcement, how can you do that? I mean, in supervised, it's very easy. You have the output, right? You have already the expected output, so it's very easy. How about the reinforcement? You know the final goal, right? You know the final goal. And in order to reach the final goal, you have two things to calculate. Something called reward and something called value function. Something called reward and something called value function. You always want to maximize the value function. How would you maximize the value function? It's the, let's say in the example of the robot, it's the action that will get you closer to your target. As an example, if you're doing robot navigation, okay? So now, again, in order to do that, you need to calculate a reward and then to calculate a value function. And when you do that, you're gonna be able to answer the accuracy, or what you have asked now. Beautiful questions, Hassan. That's really nice. I'm sorry I wasn't able, I will answer them completely by mathematics and everything when the session comes, because those two questions are huge, whether it's unsupervised or reinforcement, okay? Now, before I move on, are you guys following? Did you now know about supervised learning, semi-supervised, unsupervised, reinforcement? Are they all clear? Are you sure? Especially those who are having a GP1 defense soon. Okay, now let's go for the supervised learning. The idea behind it is as follows. You see, you give the training data, okay, it's a raw data that you injected to the system. You do something called feature extraction. By the way, the machine learns feature. So as an example, if you want to feed your face to a neural network, so the neural network learns your face, right? Your mobile doesn't really save the whole picture of your face and stuff. It gets features. So, the distance between the two eyes, the length of the nose, the thickness of the lips, the width, and so on and so forth. So you get features, you extract features out of what you want to do. I will teach you how to extract features later before we talk about neural networks, because regression, you already have the features that you want, okay? Then, based on the features you extract, okay, Heather, all right. Okay, I'll be posting the session on YouTube anyways. Okay, based on the features you have, okay, you do the training. Okay. After you train, you evaluate the model. Okay, is the training enough? Did you get the result you want? Most probably no. You know, so you need to go again and again and again until the error you get is very tiny, acceptable. Okay, you're not going to be getting zero error, by the way. When you get the acceptable error, now you can go for prediction. The system is really ready. You get the data, you make feature extraction the same way you did it in the train. You feed it to the system will give you the label that, you know, tells about the information. So as an example, if you want to identify the animal, so you feed features, the dog features is like this, the cat features is like this, and so on. And then when you train that, when you feed the neural network with a dog, it will tell you it's a dog. When you feed it with a cat, it will tell you it's a cat. You tell me it's very easy. No, it's not at all. And you cannot program it, by the way, any other way. Why is this? Simply because I didn't tell you that the dog will be in the exact same position, in the exact same distance, in the exact same color, and so on. No. You will train the neural network about dogs. Now you give it a picture of any dog, and it should be able to recognize it as a dog. Any position, standing, sleeping, rolling over, whatever. Okay? You feed that and you get the results. Okay? All right. Is this clear so far, everyone? Is this clear? Ladies, gentlemen? Perfect. Perfect. Now, unsupervised learning, however, is very different. It's very different. You get the data input. Okay, you have a learning algorithm here. Look at this. What is this? Unknown output. Unknown output. Okay, and then you, for this, the learning algorithm works and it does clustering this way, as if it's filtering the data. Okay, how and based on what I will show you. Okay, when we start talking about the unsupervised learning. Reinforcement learning. The reinforcement learning, as I mentioned, it's very different from what we have seen so far. Okay, it has nothing to do with supervised or unsupervised. When people mix between this and the unsupervised, it's very different. Look at that. You have to have an environment, okay? You have to have agent. I don't know if you guys see the mouse. Am I pointing out for something that is...
Yes, doctor, I can see the mouse.
Oh, you see the mouse? Okay. So for this mouse, sorry, for this model, you have the agent. The agent could be something like, you know, a robot or a software agent that works in Bitcoins. So you have an agent installed in your mobile, and it watches the market and decides whether we need to sell or buy. Or so the agent gets the state of the environment. What is the state? Depends on your application. Depends on your application. So if you're doing, as an example, you want to model an elevator, you know, then the agent will recognize how many people are there. Can I actually prevent people from coming into the elevator again, or is there enough space, and so on. If you have an e-host in a restaurant and you want to meet people and drive, like, you know, walk them to their table and so on, so you need to recognize which tables are empty, which tables are full, how you're going to be moving those into the table and so on. So you observe the state of the environment. Based on the state, okay, you're going to be choosing the best action to be applied. Okay, you see here selection of an algorithm. It's really, you know, the best action. And then look at that. When you choose the action, what you do is apply to the environment again. Okay, and then measure what happens. Was it really a good choice or not? If it's a good choice, you increase the reward of selecting this action in this state. If it was a bad choice, then you give a negative value for this action when you are in this state, and so on and so forth. The agent learns by itself. All you need to do is tell the agent which actions the agent can choose among, and leave it, and it will work by itself. By the way, those like that reinforcement learning, I'll show you how to programming in Python. All of them, you will program them in Python. But this one, at least until now, I haven't found a library for it. So most probably I'm gonna be showing you how to program it from scratch. Most probably, if I don't find a library for it. So this is the reinforcement learning. Okay, are we good, everybody? Shall I continue? Anyone has any questions? Anything that is not clear? Python, by the way, okay, is the language of the future. Okay, Python is the data science language. Python is the artificial intelligence language. Python is now, you can actually program mobile applications using Python, by the way, by importing one library, and it will allow you to adjust, do an application that suits any mobile. So if you're doing mobile applications, also Python. Okay, if you're sorry about that. If you're doing web applications, there's Django, which is also Python. So Python is really, really, really important language. If you learn it, you know everything. You can do everything, okay? I know it seems that it's a really weak language and so on. It's a very powerful language, okay? If you wanna be in the game in the coming 20 or 30 years from now, you should be learning Python very well, okay? I can say it loud and clear. If you learn Python, you can be jobless for the coming 20 or 30 years, okay? Now, how about the regression? Let's start with the regression. I'm gonna now go deeper a little bit about the algorithm, because those are philosophies, right? Those are different philosophies. Now I'm gonna be going deeper with some algorithm. Look at the regression here. This is the simplest regression example. What do we do here? You have data, okay? You have data everywhere, as you can see, okay? The red and the green. And you want to find the straight line that goes through those data by minimizing the error. What is the error? It's the vertical distance between any point and the line. By vertical, I mean when you draw a line from the point to the line that you see with the slope, it will give you a 90-degree angle, okay? So, see, you have here a distance from every point to the line. You sum them all and you want to minimize that. So you want to find the line that will actually minimize those kind of errors. When you do that, you have a model. Just imagine that this regression is for the x-axis would be the space, the area of houses, and the y-axis would be the price of the house. So basically, it's the price with respect to the area. And now you want to predict the price of a house that you want to buy. Okay. How would you do that? First, the system needs to learn. Is this system trained? Yes. Look, those kind of points are data items. So it tells you when the house has this area, like space area, you know, you have this price. If you have this area, you have this price, and so on and so forth. Okay, this is just imagine the data is like that. It's clearly the data doesn't really represent the price against the space, the area. It does not. But just imagine. So now you got this line, and this line represents the model, the area price model with the minimum error. Now I want to buy a house that has an area of 3,000 square foot. What would the price be? You know, so I put here in the x-axis 3,000 square foot. I will get in the y-axis the price. Okay, the price. Lazy language. Yeah, well, it's see, yeah, you can say that. It's a lazy language, the Python, but it's very strong. Very, very strong. So now, you know, when you have those kind of data points, you can train the system on it. This is, by the way, supervised. This regression is supervised. So basically, how would it be supervised? Look, every point here, what does it represent? The distance, or sorry, the area of the house with respect to the price, or the price with respect to the area, right? So what did I give the system here? I gave the system the input, which is the area, and I gave the system the output, the price. Do you see? So this is clearly supervised. But when I give the system all those points, okay, and then I can figure out an equation of a straight line this way. Why is it a straight line? Because it's a single variable, as you will see it later, okay? That actually minimizes the error of all data items. Now you got the model. Now when I ask you, I want to buy this house, okay? What would the price be? Then you can tell me, based on the statistic that we have, the price would be around this much, okay? So this is the regression. You predict the price, okay? The single variable that you see here is nice as you know, a model, as a concept, but in reality, you don't have really single variable, right? When you want to predict or we do forecasting, it's really the pressure and the, let's say, the humidity and the wind and the time of the day and the month and the day of the month and many, many, many other variables that you would use, right? Okay, which I will teach you next session. All right. Now, that's what I was talking about, all right? If you have multiple regression models, you have something like you want to see the job performance of certain employee, okay? So you see the motivation that this employee has, if you can measure it, the social support, how intelligent that one is, and then this you can give you an outcome of this model, okay? So this is a regression of 3 variables. Here, as an example, if I go back to here, you can now say, yeah, I can have really the square foot of the house, but in 2 different areas. So you could have 2 totally different prices for the same house area. Yes, you're right, absolutely right. And that's why you need to add now the area, how old the house is, how many rooms the house have, how many bathrooms or, you know, the house has. Does it have a basement or not? Does it have a garage or not? And so on and so forth. Okay, so all those that contribute to the price of the house need to be fed. By the way, everything that I add, adds another dimension, right? So more than 3 variables, like 2 input variables and 1 output, you will not be able to visualize it. Got the idea? Because we only can see in 3D, right? So you can now say the area and the the area and where the house is, as an example. Okay, more than that, you can calculate it and predict it, but you cannot visualize it the way I'm showing you now for this. So as an example here, do you see this? This is an example here, noisy data. Look, when you calculated that, you got a shape like this. So this, now it's not a straight line. This equation is the equation that shows you the minimum error between those data. So now when I ask you, I have this X, how much is the Y? You will get it precisely. Okay, this is called nonlinear regression. Nonlinear, of course, it's nonlinear. This is linear because it gives you a straight line. By the way, you can have a linear regression with multiple variables. That's not a problem. Okay. Okay. Before I continue, any questions so far? Is it boring? Did you guys get bored? How are we so far?
No, doctor, not at all.
Okay, great. Anyone? Are you guys following? All right, let's continue. Ali Qutb, are you there? Are you there? Okay, perfect. All right. That's my son, by the way, guys. So we're gonna be talking about the artificial intelligence, the artificial neural networks. Okay, what is artificial neural networks? Before I talk about the ANN, the artificial neural networks, I want to talk about first the neural networks. What is it? I can say without doubts that every huge advancement that happened in the artificial intelligence happened because we imitated something that exists in the human body or the natural system in general. So let me give you an example. If you want robots to cooperate together to do certain common tasks, how did we do that? We studied how a swarm of ants or a swarm of bees act. And then we imitated that system. We got a very successful swarm of robots. By the way, that's how we call it. Swarm of robots, okay? Or swarm of agents in general. It doesn't have to be an actual robot. It could be a software piece. But they're working together the same way how bees and ants work to give you the same performance that those give or have. Okay, if you want to solve a very complex problem, so we do something like we imitate how the DNA works and give you many different solutions and so on. And this is what we call it genetic programming. If you want to recognize images, right? You want to recognize images. You want to recognize different situations in a way that you do it fast and accurate and so on. How do we do that? We imitate the brain. We imitate the brain. Okay. So how do we imitate the brain? We have this. This is how the neuron looks like. This is the actual neuron, okay? This is the actual neuron. So the actual neuron looks like this, all right? This is the black one that you see, which is the cell body, is the computational part. This is the computational part, all right? And what you see here, the orange one, is what gives you the output, okay? Sorry, the input, it gets the input, right? And do you see those hands of the cell body? Those are, you can distribute the output to other stuff. Here, before I move on, what you see is you, basically. This is you, all right? So everything you have experienced, every memory you have, everything that you hated or loved or liked, every exam you have bad memories about, every professor you don't like, every memory you have is stored in those cells, okay? Your brain, by the way, has 100 billion of those, okay? 100 billion of those. And that explains why when you see an image, you recognize it right away, okay? I forgot to put something I already did with my students. It's kind of an experiment to show you how the neural network, works, or how powerful it is. Okay, let me show it to you. Let me get this one. It looks cool. Just a second. Here. Okay. I'll be sharing now the whole screen so you can see something. Let me share desktop 2. So now look at this. What is this? What do you guys think that is?
A watermelon chair.
Okay. So it's not edible. Can you eat it?
No.
No, right? Have you ever seen a chair that looks like a watermelon before?
No.
In reality, okay, perfect. How did you know, as soon as you looked at this, that this is not a watermelon to be eaten? It's not edible. It's a chair that you can use to sit on. How did you know that? Your neural network.
Because we know what a watermelon looks like and what a chair looks like.
Well, yes. The strength of neural networks has what we call approximation, So you literally approximated the thing that you see. Yeah, it looks a watermelon, but it's more of a chair. So now you know it's a chair. This is how the power of the neural network is. That's how neural networks work. And that's why if you want your machine to be that intelligent in recognizing images, in dealing with certain situations and so on, you need to equip this machine with a brain, with a neural network. Okay, everybody, so far so good? Did you get the example? Yeah, okay, perfect. Now, the artificial neural network now. As I mentioned, you know, we fake everything, like not we fake, but we imitate the natural system in order to make sure that our system is really, really successful. So how do we do that? Look at this. This is how the artificial neuron is. The actual neuron is here. The artificial neuron is here. Those are the inputs. In the middle here, it's the body of the neuron. And here you have the output. Okay. This neuron gets inputs, as you can see, x1, x2, x3 until xn. Every input is multiplied by a weight. What is this weight? What is it? It's those, do you see? Those kind of weights here. Those are the weights, okay? The weights. All your memory, everything that you have learned, the language you speak is in those neurons, distributed all over the 100 billion neurons in your brain, okay? That's why, you know, people can get hit on the head or something and they forget stuff, but they still remember stuff. Why? Because all your memory and stuff are, you know, distributed all over all the neurons. Some of them might be affected, but the others are still there. Okay. So here. But
first, you'll have to unlock your device.
Okay, thank you. Yeah. Now you have here the inputs. All right. You have the weights, and then how does it work? Every input is multiplied by the weight, and all of them are summed together inside the neuron body. Then when you sum them up, you go and send it to a transfer function. What is a transfer function? Not a function, mathematical function. We have fixed functions, by the way, for neural networks. I'll show them to you. You can have your own function, of course, but I mean, the functions that I will show you them now are the ones proven to work best with the neural networks. Okay. And then after you do that, you get an output. Okay, you get an output. Those are the transfer functions, all of them, not all of them actually, those are just some of them. The most commonly used is what we call sigmoid. Okay, the sigmoid one, right? Here it is. This is the sigmoid. Okay, so this is 1 divided by 1 plus e to the power minus the weights transpose x multiplied by x, which is the vector of input, plus bias. Forget about this. This is not important. When I start programming them in front of you, you will understand each and every component of those. I just wanted you to know that the output is being calculated here. See, the output is being calculated. Okay. Y is the output, of course, and X is the inputs, you know, and B is a bias, something I'll talk about. Now we have multi-layer neural networks. What is this? Each and every circle that you see is a neuron by itself, is a whole thing like that. Okay, I told you, in reality, you have 1 billion neurons, right? In artificial neural networks, you don't have 1 billion, but you have a lot of thousands, okay, that look like that. And in reality, the artificial neural networks is divided into layers, okay? Let's assume that this one is for, what do you call it, an image or something, okay? The image has dimensions of 28 multiplied by 28, okay? So what is the input layer? It's going to be 784, which is 28 by 28. every one of those could have a value from 0 to 255. Don't worry about this. The most important thing here is to know that this is mathematics. There's no magic here. Okay, there's no magic. It's literally mathematics. Okay, so you have here the input neurons. The input neurons is always the number of inputs or features. You remember the word features that I talked about? So the number of features you have that you're going to be feeding to the neural network. Then the processing happens in the hidden layer. Okay, how about the output layer? The output layer here is how many categories you have. If you want to classify how many, the first one, if you get the maximum output in number 0, 0 is a cat, 1 is a dog, 2 is a fox, as an example, and so on. So you feed the image. If the image is a cat, you will find that neuron number 0 will give you the highest number, and all the others are much, much less. There is other designs that says winner takes all. What does it mean? If it's a fox, you're going to be having one output here at 0, everybody else is zeros. Okay. Anyhow, so you can have here the output. The output is usually from 0 to 1. Okay, like probabilistic. But there is an approach called winner takes all. If it's winner takes all, then if it's a cat, 0 will give you a 1, and everybody is 0. If it's a dog, neuron number 1 will give you a 1, and everybody else is 0. If it's a fox, then number 2 will give you a 1, and everybody else is 0, and so on. Okay? If it's not a winner take all, then you will find that if it's a cat, neuron number 0 will give you, as an example, 0.8. And then the other 0.2 will be divided all over everybody else. Of course, assuming that you chose the right features, right? This is supervised learning. Okay, if the teacher is bad, say goodbye to the students, right? So the model that you're feeding here, the model that, like the data that you're feeding, have to be very good, so that you expect to get the a good output. Okay, this is supervised learning. You are teaching the neural network. If you get this output, this is my, if you get this input, this is your output, and so on. Okay, so you gotta feed the neural network with the proper data and the expected output. Okay, in order for you to, have a very well-trained neural network. Okay. One of the examples of the neural network is back propagation. It's one of the algorithms that you train the neural network for. Okay, I just wanted to show you a very quick example about it. I'm not gonna go into any details now, so you're not confused. We're gonna be taking it step by step. The next time I'm gonna be going for regression for sure. It's very important. It's especially for those who work in data science. Regression is one of the big things. So I'm gonna go for regression next time, and then we continue. So in one day, I'm gonna be showing you the back propagation in details, and I'll solve it for you using hand. I'll show you how the forward phase happens and then the backward phase happens. But briefly, look, you want to train this neural network. How will you do that? Get the output, feed it to the x's. Okay, until you get the output from the y's. I told you this is supervised learning. So every neuron has an actual output and an expected output. The expected output is the output that you should have got if the neural network is well trained. And the actual output is what you actually got. Based on those two, you calculate error. How? I will show you in detail. It's very easy, by the way. Please don't panic. Very easy. Okay. When you calculate this error, we go something called backward chaining. You fix the neurons all over the network until you go to the input layer again. And then you feed it again. You calculate the error again. And then You go backward and fix the neurons, the weights. That's what you're fixing, the weights, until you go to the input again. Feed it again. You get another error, and so on and so forth. The way it should be that every time you fix some error and feed again, you will get an error, but less. Feed it again and again and again and again until your error that you get out of those neurons would be accepted by you. And now the neural network will achieve what you want to achieve. Okay? All right, those of course are like, you know, example of the equations and so on. I don't want you to worry about this for now. When we go for the neural networks, I'll show it by hand and then I'll show it how you can program it using Python, okay? All right, okay, we took around 90 minutes. Are we all good so far? Are we good so far? Everybody?
Yes, doctor, everything is clear.
Okay. All right, index from 1 to 5. 5 is interesting, 1 is boring as hell. How would you evaluate the AI so far and the machine learning?
100.
Okay, that's really great. Okay. Okay, that's amazing. All right, who wants to attend again? Who wants to continue with this?
Me, please.
Okay, great. Great. All right, okay. So, as you all know, next week is gonna be the winter break, all right? So we're gonna be continuing our very first session after this, which is gonna be totally for the regression, very important for computer engineers and computer scientists. Okay, we're gonna be doing the regression the very first weekend after we come back, okay? After we come back, right? This lecture, for my senior projects, please, I uploaded some papers about introductions about neural network, introduction about machine learning, and so on and so forth. Read it by heart, okay, for your defense, okay? And I'm gonna be uploading this lecture as well to YouTube, and you know, probably I'll put it as a link to your page if you wanna go back to it to remember something about it, okay? Everybody, whether you're students or a graduate, if you need anything about that, you know how to reach me on Twitter, ask whatever you want, and I will definitely answer you, okay? I will see you the very first Saturday after we come back from the winter break. You will find an announcement on Twitter, okay, that we're gonna be starting again this, all right? Thank you, everybody. It was so nice having you all. If you have any questions, send me on Twitter, please. Perfect.